To introduce the idea of vectors, I'm going to start actually by showing you how do you begin to explode subdivided surfaces by not just scaling the sphere's faces, but actually moving them. And that's the key operative term is move, because move is going to be our first component or first node that actually operates off of a vector, which has direction and magnitude in the unit of distance in this case. Okay, so to get us started, let's go with a subdivided sphere. So go into surface and primitive and drop in a sphere.
Does it make a difference if you work in inches or feet on right?
For this exercise, I don't think it matters, but I like to try and work in feet, but thank you for the reminder. I am working in feet. So for our sphere, you could either override the origin and place it somewhere else with a point somewhere if you'd like, or you could just leave it at the origin for now. I'm going to leave it there, and I'm going to set a radius for me to work with. So 0 is less than 10 or so, less than 20. I'm just guessing right now. So here we are, my sphere in space at the origin, all good to go. So we're going to subdivide the surface of this sphere because if you look at the output, it actually is a surface. It says resulting sphere, but it has the icon of a surface, right? So it can read as a polysurface or as a BREP. Well, you'd have to convert it to a BREP. But so when you look back at what we did last week, we're going to reestablish a subdivided domain is essentially what it is. So you go to math, domain, and you go to divide domain squared. And we'll place it down here. Domain. And we can plug the sphere into the I input, which is our base domain. And then we're going to tell it how many subdivisions we want. So for me, I'm going to keep the same. I'll just keep the same slider. It'll do the job. And I'll put that in U and V. Yeah.
Which divide was it?
So the question was, which divide was it? It's divide domain squared. So you go to math, domain, and it's all the way down the bottom, divide domain squared. So we did two types of domain work last week. We did a construct domain where we told it minimum, maximum based on a surface. In this case, we're not constructing anything. We're just breaking it down. Okay, and then the other component to this is actually creating a trimmed surface with isotrim. And if you recall, that's under surface utilities, and it's called isotrim. But remember, when you drop it in, it's going to say subsurf, as in subdivide surface, which is kind of confusing because we're actually dividing the domain with math with this, or we're dividing the surface up using a domain establishment. But then we're plugging it into isotrim to actually trim it up into subdivided surfaces. So yeah, similar to pixels, very similar. So we're going to plug the domain, right? Even though this says S, don't let that confuse you. Even though this says S, if you hover over it, that icon means that it's a domain. And so we'll plug that into the D input of subdivide surface. And then we plug our surface into the top. Okay, so go here and put a tag on there, surface utility. And this, let me just kind of reiterate here. These three components, those three nodes, they're sort of like the trifecta of subdividing surfaces. You will use these three so often that it'll drive you crazy. Well, and this is obviously variable, but you're going to have a surface that plugs into these two. So really, I guess it's just these two, but you get the idea. Okay? So just visualize that for what it is. All right, so I can turn my original sphere off, and then you can see here that we actually have our sphere fully subdivided, and then we can begin to work with it. So Do you recall how we begin to break it apart into its component parts? Anyone? Which tab it's under? All right, well, we're actually already on the tab that it's under, Surface, right? Remember?
Oh, yeah, it's a little fire thing.
Yeah, a little fiery thing, yeah. Deconstruct BREP, or if you think about it in terms of exploding, right? You're exploding it into its component parts. I think that's what that icon is for. Though I'm not sure. All right, so we drop that in and we plug it in. That's not how you spell it.
Close enough.
All right. So we've got all of our component parts now, right? So here's where it really starts to get crazy. What I want to do is increase the size of this sphere, but not the size of the cells, right? I want to move them away from the center. So let's my first thought when I was running into this, I actually thought, well, why don't I just scale it? So let's take a look under the Transform tab. And we're going to look at, under Affine, this one right here, it's called Scale. It says it'll scale an object uniformly in all directions. So let's drop that in and take a look at it. It's asking for a couple of things. It asks for a geometry, which would be the sphere, center of scaling, and then the factor, right? So this is a multiplier. So when I plug in my faces to the scale, look at what it's doing. It actually assumes the center point of the sphere at first, and you can override that if you want. But then the scale factor is a 0.5, and so it made it smaller. But if I change that, let me make it a 5.
Where's this?
Scale is under Transform, Affine. Okay, so if I make this a 5, what you're seeing here is that it's not moving the cells out like maybe I thought it would. It's actually just scaling up all of the surfaces referential to the center point, and so it's not creating a gap that I want in between each cell. So that's not the route I want to go. So I'm going to get rid of scale. Scale isn't right. What I truly need to do is move them, because scale isn't, the scale of its distance from the center point is going to make all of them bigger. I want them to be the same size, and I want them to slide away as if I'm taking it off. Okay, so that would actually be under Move, and it's under Transform, Euclidean. All right, so take a look at, just real quick, take a look at all of the commands here that are under Euclidean. They're all essentially some form of coordinate transformation. So it's not necessarily something like under Affine where you're changing the properties of the form itself, but you're doing something that translates it across space in some way. Okay, so that's the difference here. And morph also is another one where it's changing the geometry instead. So under Euclidean, we're going to pick Move. And let's see. So under Move, it's only asking for two things. It's asking for the geometry, and it's asking for the translation vector. Okay, so this one is not intuitive. Okay, it has a vector inherent to its, standard properties, right? And what does it say? It says 0, 0, 10. So thinking ahead, what do you think it's going to do when I plug in my geometry to this Move component? Yeah, Carl.
What's it going to do to the form? Or?
Yeah.
Oh, it's just going to move it.
Where?
X and Y wise. Or Z.
Where's it going to move it?
If you either in the X direction or Y direction, right? Isn't it?
It's one of them. Which one?
Oh.
Z. Yeah, it's going to move it in the Z direction. Right? X, Y, Z. That's the order. So when I plug this in, whoops, what did I do there? Oh, what? I plugged it in the wrong spot. So disconnect. There. Okay, so it just simply moved it up. So we're getting a little bit closer, but we're not quite where we want to go. What we have to do is actually change this vector format to read all of the surfaces from the center point, and then we're going to multiply the distance between it. Okay, so that essentially just looks like this. I'll leave the geometry there for now, but to change the translation vector, we need under vector, it's called vector 2 point, and I think it's under vector. Yeah, vector 2 point right here. So let's place it here. This is going to be our end point, really. Vector 2 point is going to be paired with a multiplier. But let's take a look at how we're going to communicate with it. So it's asking for a base point. It's also asking for, well, the secondary point, which essentially would be what? Think back to what kinds of data we have available to us when we deconstruct. We have point, line, and plane, and what subsets of those, right? Well, yeah. So when we were trying to orient geometry onto a warped surface, we used the centroid. So if we're going to move these, we probably want to move them based on their orientation at the centroid. You would think, at least when we're trying to do a uniform move. So let's. I'm going to real quickly drop in an XY plane, just so I can tie it to my sphere, and that's going to default at the origin. And I want you to understand how this works visually, so that's why I dropped that in, because it actually does borrow the origin property, but it might not always be at the origin, so that's why. So then I'll also plug that in to my origin, my base point, for vector 2 point. And then, similarly, we are going to find, oh, let me set this up for you too. This is under vector vector. And then we're going to find the centroid, and we're going to measure the distance from the centroid to the base point. So do you recall where we find the centroid? Area, right. So under surface, under analysis, it's area. And we can plug our faces in there. And we can grab our centroid from here. And then we have 100 vectors that are being output. So real quick, let me hide this and hide a couple of extra things that we don't really want to see yet. Let's take a look at it like this. Okay, so in 3D space, we've got all of our surfaces subdivided into centroids with a singular base point. Okay, so when we were doing our grid subdivision assignment, we looked at how do you visually see the subdivisions of the different component parts? How do you visually see the number? Sorry, it's been a long day. How do you visually see the numerical order of each of the component parts when you subdivide it? So we're going to look at display, and this time under vector, we're going to click on vector display. Anchor point. All right, and it's going to borrow the anchor point, right? And then our vector itself, well, yeah, the vector to preview, which is that. All right, so this is what I want you to get to at this point, is that you're reading and visually able to see all of the vectors that you're then going to manipulate. Are there any questions?
What's the A connected to?
The A is connected to the origin. So let me actually kind of pull that up a little bit. Let me compact this so you can see.